Hello. Good afternoon, my dear student. Today we will discuss about some important parameters of series resonant circuit. In last class, we have discussed about the concept of a series resonant RLC circuit, series resonant RLC circuit, and you know that resonance is a phenomenon or is an event that occurs in a RLC circuit, series RLC circuit at a particular frequency, and that frequency is known as resonant frequency. So resonance is an event or phenomenon that occurs in a series RLC circuit when the frequency of the applied signal or applied voltage is equal to the resonant frequency. Now one question comes in your mind or in our mind, that what is resonant frequency? The resonant frequency, you know that the frequency at which the magnitude of inductive reactance and capacitive reactance become same. Inductive reactance and capacitive reactance become same. That frequency, the corresponding frequency, is known as resonant frequency, and you have derived in last class the expression of resonant frequency f r equal to 1 by 2 pi root over LC. If we consider omega naught L, the reactance of inductance omega naught L equal to 1 by omega naught C in the reactance of capacitor. Okay, and if you take omega as a common, omega naught square equal to you will get 1 by LC. The omega, you can get omega naught equal to 1 by root LC. So m naught, the resonant frequency, as a linear frequency equal to 1 by 2 pi root over LC. Okay, no problem. And you also know that this such type of circuit, especially resonant circuit, is applied or is used widely in TV and radio receiver. In TV and radio receiver to select a particular desired frequency or particular station or message, okay, channel. Now we will try to derive or understand the others parameters, importance parameter of resonant circuit. For example, half power bandwidth, half power bandwidth, half power points, okay, and Q factor or quality factor, okay, and their interrelation, and also resonance curve. So let me write here, everyone write it. Importance parameters are, first parameter, important parameters are half power, half power bandwidth, okay, or you denote is at HP, half power bandwidth. Then we will try to understand the frequencies, corresponding to half power point. Okay, so you just write it, a half power frequency, half power frequencies, okay, and you denote it as if if low and if high, half power, and you write here, you write LP, okay, and then we'll try to understand one important parameter that is known as quality factor or Q factor, or sometimes it is known as figure of merit for the circuit, or figure of merit of the circuit, figure of merit, okay, for resonant circuit. And we will also try to understand resonance curve, okay, resonance curve. So we will, in today's class, we will try to understand the following important parameters of a series RLC circuit and also resonance curve. Okay, and then we will solve some problems. So first, let me tell you what is resonance curve. Okay, before going to discuss about resonance curve, you tell me what is the value of impedance at resonant frequency. What is the value of impedance for a series RLC circuit at resonance curve? Okay, now we will discuss about resonance curve. So before going to discuss about resonance curve, you tell me what is the expression of impedance for a series RLC circuit at resonant frequency. When your circuit okay, uh, when resonance occurs in your circuit, when resonance occurs in your circuit, then what will be the value of impedance? Anyone tell me? At resonance, what is the expression of impedance for series RLC circuit? For series RLC circuit, when impedance reactance equal capacitive inductive reactance capacitive reactance, then R or Kodim R. Okay, right. Nivedita R, purely resistive. Thank you everyone. To Dibbojyoti Roy. Okay, thank you everyone. Your answer is correct. So therefore, at resonance, the impedance of a series RLC circuit is R. Z equal to R. That means circuit is purely resistive circuit. Now you draw a curve. You draw a curve which signifies the variation of current with frequency. Okay, if you draw a curve corresponding to the variation of current for a series RLC circuit with frequency, if you change the, the frequency of the supplied voltage is changing with time for this circuit. Okay, for this circuit, the AC resistance, we have considered AC supply voltage, and the frequency of the AC supply voltage is changing or is varying, but its magnitude or amplitude is constant V. Okay, so now if you draw the variation of current for a series RLC circuit with frequency, then what type of curve you will get? So you know that at resonant frequency the circuit becomes a purely resistive circuit. Therefore, the current through this circuit at resonance is nothing but equal to V by capital R. Okay, so let me write this thing, then you can easily understand. So at resonance Z impedance of the circuit, impedance of R series RLC circuit, series RLC circuit is capital R. Impedance is equal to capital R. That means Z equal to capital R is Z equal to capital R. Okay. Now we can calculate the corresponding current. So current at resonance, you just write IC suffix r, IR equal to, you can write according to Ohm's law, supply voltage divided by impedance of the circuit. The supply voltage, you just write this is magnitude, you consider equal to R. Here we have considered the magnitude. Okay, you know it has a phase also, so we consider magnitude. Okay, so V by R, this V is the RMS voltage of the supply voltage. Okay, you just consider this is equation 1. Okay, equation 1. Now you consider the current. Our objective resonance curve means what? Resonance curve, you just write inside a bracket that I versus frequency. Okay, curve. I is the current through our circuit and A is the frequency of the input signal. So we try to draw a graph. Here let me draw. This is our I and this is, suppose you consider this is your frequency. Okay, your frequency. Resonance curve is a graph or curve corresponding to the variation of current through the series RLC circuit with frequency. Okay, good. This is I. So I in ampere and A is hertz. Unit of I is ampere. You just write inside bracket ampere, and this is uh, hertz, and A in unit is hertz. You just write yourself. Now you see at resonance frequency, these things happen. Current I equal to IR V by R at resonance frequency. So if you consider this point as resonance frequency, suppose let me define the resonance frequency. This point indicate the resonant frequency. Okay, F R. Okay, we have derived the expression of F R in last class. Okay, this is the resonant frequency, and you see the at resonance IR the current becomes maximum, that is V by R. If we consider of resonant frequency, so other frequency, not suppose F is not equal to equal to FR. Okay, of resonant frequency, that means on either side of the resonant frequency, what will happen? What will be the expression of current at this point? F equal to FR, at this point the current is V by R. So I can mention this current, suppose this is the maximum current, this current equal to V by R. This is the maximum current. Okay, because lower impedance V by R. Otherwise you will, for other frequency except FR, the current I equal to, you can write V by what? Z, mod Z. So mod Z equal to, you can write square root of RA square plus omega L minus omega C whole square. Okay, the impedance of the circuit is Z equal to, you just write RA square plus omega L minus 1 by omega C. Is it correct? Omega L minus 1 by omega C. Okay, we have derived this thing so far. Okay, this is square root of this term. This is square. Okay, so you just consider the superscript. It's good. Okay, because you know that impedance for this circuit you write here at resonance z equal to r, or in other frequency if is not r, then you can write impedance for this circuit z equal to r plus j omega l minus j omega l, the reactant omega l, r minus j omega l. Okay, sorry, r not minus, r plus j omega l minus 1 by j omega c. You can write it for this circuit omega c. Okay, the impedance of the circuit, z equal to real part plus imaginary part. Real part for this circuit capital R, and imaginary part the term associated with J terms, J. Okay, and reactance for inductor is omega L, and reactance for capacitance is 1 by omega C. So therefore we can write impedance for this circuit at of resonance equal to R plus J omega L minus 1 by, you just take inside the bracket J terms, 1 by J omega C. You take plus sign here. So finally you can write Z equal to, if you take mod of Z equal to what? You will get mod of Z, means magnitude. It is a complex term. You know, each and every complex terms has two parts, polar form, magnitude and phase. So you can write square root of RS square plus omega L minus omega C whole square. If you take this is upper, then it will get, you will just write here minus j, and you can write it minus j by omega c. If you take j common, then you can write omega L minus 1 by omega c. Is correct? 1 by omega c, and you take magnitude, square root of real part square plus imaginary part square. So you will get this term mod z equal to square root of rs square plus omega l minus omega c whole square. Now you tell me what will be the expression of, what will be the value of current, at of resonance frequency, mean on either side of resonant frequency, what will be the value of current. You have seen that from this equation that current is maximum at resonant frequency, but what will be the value of current for this frequency? This current you can write this equal to IR, this equal to IR, this resonant current, maximum current, or this is actually maximum current V by R. Maximum current for this circuit is V by R. Therefore, this is our maximum current. This point is maximum current. Then what will be the value of current for frequency lower than resonant frequency? I mean this region, and greater than resonance frequency, this region. What will be the value of current? The current will be smaller than the value of current at resonance frequency, because you see the numerator term is fixed V, but denominator term is different. This is only R, and for this case R square plus omega L minus omega C whole square. That means the value of denominator for this case of resonance frequency is greater than for resonant frequency case. Okay, so therefore current will be minimum for this case, means a smaller value than for resonant frequency. So we can draw the uh, you will get a curve like this. Uh, you just remove this color, background color, you remove it. You will get a curve like this, but you just okay. At resonance, you will get maximum value of current V by R, but just left hand side of resonant frequency or right hand side, I mean either side of resonant frequency, the current will be smaller value. Current is less than its value corresponding to resonant frequency. Okay, you will get, so this is the maximum current at resonance frequency, and just lower the resonant frequency, the current decreases, and upper the resonance frequency, current also decreases, because this omega L at frequency greater than FR, this omega L term will be prominent. Okay, inductive reactance. Okay, this term will dominate this denominator part, and if you consider the frequency lower than the resonant frequency, then this part, okay, this part will dominate the capacitive reactance, the reactance corresponding to capacitor. This part will dominate dominate actually denominator terms. So as a result, I will be smaller compared to IR. Okay, IR. Okay, so if you draw the curve current versus frequency, then you will get a maximum current at F equal to FR, resonant frequency, because I equal to V by R. Only R term is present in our circuit. But if you consider other frequency except of resonant frequency, then you can see that the current term actually depends on supply voltage magnitude, as well as uh, the impedance of your circuit. And in this case, impedance is not a pure resistance. In this case, impedance is the combination of resistance and inductive reactance and also capacitive reactance. And you know that for frequency greater than resonance frequency, that time omega L term will be higher compared to omega 1 by omega c term. And if you consider low frequency range, I mean less than resonant frequency, then 1 by omega c term will get higher value compared to omega L. I have already discussed this part in last class, that when frequency is less than operating frequency or signal frequency is less than resonant frequency, then your circuit will act as a capacitive reactance. The impedance of your circuit will act as a capacitive reactance. On the other hand, when frequency of the operating signal or operating applied signal or operating frequency of your circuit is greater than resonant frequency, that time your circuit will act as a impedance of your circuit will act as a inductive, as a inductive reactance. Okay, so this from this expression we can easily prove this thing. Okay, so suppose this is equation 2. Equation 2, this consider this is equation 2. This equation is 2. Okay, so from equation 1 and equation 2 we can conclude that the current of a series RLC circuit becomes maximum. The current will attain its maximum value at resonance frequency when F equal to FR and its value is V by R. But either side of resonant frequency, the current decreases with frequency because the impedance of the circuit is corresponding to resonant frequency. Any doubt? Any doubt about the resonance curve of a series RLC circuit? Why the resonance curve, the shape of resonance curve becomes a bell-shaped curve? Why? Because at resonant frequency the current is maximum V by R, and on either side of resonant frequency the current has lower value compared to resonant value corresponding to resonant frequency. Okay, now you tell me, if you draw a curve corresponding to the variation of resistance, capacitive reactance, inductive reactance and total impedance of the circuit with it, what type of curve you will get? Let me repeat this point. If you draw the variation of resistance, capacitive reactance, inductive reactance with and total impedance of your circuit with them, what type of curve you will get? You draw it yourself and let me know. Okay, now I am telling you that you draw the curve corresponding to the variation of resistance with frequency, the graph corresponding to the variation of capacitive inductance with frequency, the graph variation of inductive reactance with frequency, and total impedance. So let me write here, it's better. You draw, everyone draw the curve corresponding to resistance versus frequency. Draw the curve, draw the curve for R resistance versus frequency. Then you draw the curve for inductive reactance XL versus frequency. Frequency is the signal frequencies, and draw the curve for capacitive reactance XC versus frequency of the signal, and finally you draw the curve for total impedance of the circuit Z total impedance of the circuit versus F. Anyone can tell me what will be the shape of the curve corresponding to these three cases? Anyone can tell me what type of curve you will get if you draw R versus frequency curve, XL versus F curve? This is the resistance of your circuit. You write inside a bracket. R is the resistance. R is the resistance of the circuit, and F is the frequency. Frequency of the applied applied signal, maybe voltage or current, no problem. And for this case, XL is the inductive reactance, inductive reactance, that means omega L, inductive reactance omega L, nothing but omega L, you know, omega into product of omega angular frequency and the value of inductance omega L. Okay, inductive reactance, and A is same. A is the frequency of the applied signal, and for this case XC, capacitive reactance, that is XC equal to, you can write 1 by omega C, 1 by omega C, magnitude 1 by omega C. And for this case total impedance of the circuit, total impedance Z, impedance Z equal to, you know, this is R plus J omega L minus 1 by omega C. You know it. Now you draw the curve for these four cases, and you tell me what will be the shape of the graph. Anyone? For resistance to the graph is somewhat, oh no Saiba, for R versus F it will linear. Thank you. Parallel to Nivedita, you are right. Because R is independent of frequency. R is not a function of frequency. So therefore, whatever the value of frequency, R will be a same value. That means it is constant over the whole frequency range. So you will get a linear or straight line parallel to x-axis. I repeat this point. Resistance of this circuit is independent of the signal frequency. It does not depend on the value of frequency. Whatever the value of frequency, R will be a constant value. Xi, Xc, it is somewhat exponential, and for total impedance it is right, Saiba. Now you are right. What about other student? Write your answer in your chat box. Okay, so therefore this curve will be, let me write the answer. The curve corresponding to R versus F is a straight line parallel to x-axis, parallel to F. The curve corresponding to R versus, corresponding to R versus F is a straight line parallel to frequency, because x-axis, along the x-axis we have considered frequency. Nivedita, your answer is correct. Saiva also correct. Right answer of this question. Other student, please write. Okay. Nivedita, Saiva, anyone? No. Write your answer. Okay. You see the R is in the curve corresponding to R versus F is a straight line parallel to frequency, because you just write this point, because the value of R is independent of, but does not depend on, the value of R does not depend on frequency of the signal. frequency of the applied signal. Okay. But if you see the reactance of inductive reactance, you see a term omega is associated with it. That means it depends on frequency. And if you see the capacitive reactance, then you can realize that there is also another frequency term associated with this reactance, that is omega. So if omega term is associated with any inductive any reactance or impedance, that means that particular variable is a function of frequency or depends on the value of frequency. So for this case you can say, Saiba, you have made a mistake. XL is linear, right? Right, Nivedita, XL is linear, X it is exponential, Z it is parabolic. Saiba, you just correct one. XL inductive reactant is linear, because you see that the reactance, this term is proportional to frequency omega. Let me write here for your better understand. You see that for this case you see that xl is directly proportional to omega frequency, I mean frequency, directly proportional to frequency. And you see this is look it like a straight line equation, y equal to mx plus c is 0 for this case. So you will get for this case xl is directly proportional to omega. That means the curve therefore hence you just write, hence the curve corresponding other student try to understand the point corresponding to XL inductive reactance versus frequency of the signal is a is a line. Okay, is a linear okay, is a linear curve. So you just write is a linear curve. Okay, you will get the, for this case you will get the, for if you draw it, let me draw these things here. If you draw for resistance versus resistance versus frequency, so you will get like this. This is your resistance, this is frequency. You will get a curve like this. This is R value. Okay, this is R value. So this is corresponding. For this case, for you just write the x-axis F and y-axis R. And for this case, XL versus F, you will get a curve like this. This is F. This is the XL, and you will get a linear curve. Look like a ramp function. Look like a ramp function. Increases with increasing time. For this case, increases with increasing frequency. So that this actually XL. This denote the curve XL. XL, capital L. Sorry. And now you can write. You can write, and this is frequency. Everyone right, and this is F. Okay, similarly this is R, this is R, oh, R, R, capital R, and along the x-axis you just write frequency F. Okay, and for this case you see that for third case the reactance is inversely proportional to frequency. So for this case, Xc is inversely inverse inversely proportional to frequency f omega. Okay, omega is nothing but omega equal to, you can let me write here, omega equal to 1 by 2 pi f. 2 pi is a constant term, so you can write uh, proportional. So omega equal to 2 phi 2 phi f. Okay, don't make any confusion between omega and its omega equal to 2 pi f. For this case, x is inversely proportional to f. Therefore, okay, capacitive reactance, okay, increases when omega decreases, and capacitive reactance decreases when omega increases. That means you will get an exponential curve. So the curve, therefore the curve corresponding to this is an exponential curve. The curve corresponding to xc versus f is an exponential curve. It okay? Exponential curve. If you draw, then you will get a curve like this, exponential curve. Okay, and for this case, you will get a parabolic curve. You draw it yourself. And correct it. So this is xc, and you will get a curve, exponential curve. How do I draw it? Any values is there? Exponential curve. You draw it yourself, you will get a curve. No, you will get a curve like this, you will get like this a curve. Okay, no, no. I actually, you draw it yourself, you will get a curve like this. No, this will be exponential, not a straight line. You draw it, and for this case you will get a parabolic curve. For this case you will get a parabolic curve. At resonance frequency you will get minimum impedance, and other side means either side of resonant frequency you will get maximum. This case you will get a parabolic curve. This variation will give you a parabolic curve. This graph the graph corresponding to z versus f is parabolic. Okay, is a parabolic curve. Any doubt? Everyone, draw it yourself. Any doubt? XL is linear XL. Any student? You have any doubt regarding the variation of resistance versus frequency, inductive reactance versus frequency, capacitive reactance versus frequency, and total impedance of your circuit versus frequency? Okay, so resistance versus frequency is a straight line. Okay, and impedance versus wave is a linear line and look like a ramp function. And for resistance case, it is constant for all frequency range, over the whole frequency range, and in this case it is directly proportional to frequency XL. So frequency increases, XL increases. On the other hand, XC is inversely proportional to frequency. If frequency increases, then XC will decrease. On the other hand, if frequency decreases, Xc increases. So therefore, you will get an exponential curve. And for impedance, you will get a parabolic curve at resonant frequency. When F equal to EFR, you know Z equal to R, minimum impedance. And on the either side of the minimum impedance value higher actually compared to R minimum value. So therefore, you will get a parabolic curve. Okay. Now let me tell you one important uh, parameter, that is half power bandwidth. Half power bandwidth. Half power. Any doubt? Any doubt regarding the resonance curve? Half power bandwidth. You just denote it BHP. Half power. Any confusion regarding the resonance curve? Orkodib okay. What about others? Resonance curve. What is resonance curve? What is the variation of current with frequency? Okay, with frequency, and the variation of different impedance, capacitive reactance, inductive reactance, resistance with frequency. In this context, let me ask you a question. If you see, for this case, this is R, V by R, resonant frequency. If you increase the R value and decrease the R value, then what type of curve you will get? Everyone look at the resonance curve. Resonance curve means the variation of current, for the series RLC circuit with the frequency of the applied signal. In our case, applied signal is an AC voltage. The magnitude of AC voltage is a constant, that is capital V. Okay, VRMS, I mean capital V, not capital V. Is its root mean square voltage. AC case we always consider root mean square value by R. So now my question is that if you increase the R value, then what type of curve you will get? A resonance curve. And if you decrease the R value, suppose this R value, you increase this R value equal to, for example, suppose 5 ohm or 10 ohm. If you increase, suppose make it 20 ohm or 5 ohm, then what type of curve you will get? Or very large, very small compared to this. You just consider this R value. You just consider R value. R value is medium for this case. Let me write here. In this case, R is medium. The value of R is, in this case, the value of R is medium. Now, if you increase, make R is very high. R is very high. Then what will happen? And R is very small. And R is 0. And you consider R is 0. Then what type of curve you will get? This curve corresponding to R is medium. R value is medium value. If R is very high, then what you will get? If R is very low, then what type of curve you will get? R is 0. R is 0. Then what type of curve you will get? Anyone can answer this question? Resonance curve, you know, this is nothing but the variation of the circuit current with respect to the applied signal voltage, and it look like a bell-shaped curve or symmetric curve. It has a maximum value at F equal to FR, or resonant frequency. On the either side of resonant frequency, the current decreases. the current decreases. And you have noticed that maximum current depends on two terms, V and R. If you consider V is fixed for a signal, its frequency changes for AC cases. We have considered here the signal amplitude or RMS value is constant, but its frequency is changing with time. So therefore V is constant. Therefore maximum current of the signal is inversely proportional to R. Inversely proportional to R. So if R increases, then IR decreases. Maximum value decreases. If R decreases, maximum value increases. Therefore your curve for R increases, your curve corresponding to increment of R will become a peaked or sharp curve. If your R decreases, then what will happen? R increases, then you will get flat curve. Sorry, let me write here. It's better. Here you see. You write here. You write here. You write after this slide. Everyone, solve this one. What type of change will occur in this curve? You see, IR resonant current or maximum current equal to V by capital R, where capital V is a constant. Okay, so therefore we can write, therefore I maximum current or IR is inversely proportional to resistance. If resistance increases, if R, the value of R increases, then we will get IR will decrease. Okay, then we will get a flat curve. Then the curve becomes a flat curve if R increases. That means here you write within the bracket very high value, very large value. Okay, for very large value the curve become a flat curve. Okay, and if R decreases mean R value very small value, then the curve becomes a sharp curve or peaked. The curve becomes a sharp curve. Okay, and if R 0, then what you will get? If R 0 means 0, V by 0, infinite. So current goes to infinite. The maximum current goes to infinite. Okay, so for this case you will get a flat curve. R is increases, R decreases, you will get a peak curve. Okay, or sharp curve. R is small, so V by R, IR will be high than the medium value, and IR will be smaller than the medium value for R is very high. And for R equal to 0, your current will goes to infinite. Therefore, you will get a curve goes to infinite. When if R equal to 0, then IR will be tends to infinity, tends to tends to tends to infinity. Everyone try to understand this point. Infinite. Okay, infinite, infinite. Therefore, the resonance curve, the shape of resonance curve is changing with the different values of resistance. If resistance value is high, then the curve becomes a flat curve. If resistance value is low, then the curve becomes a peaked curve or sharp curve. If R is 0, then current tends to infinite. Actually, I am telling you this point because this concept is required for calculating the half power bandwidth or to measure the selectivity of your RLC circuit. As in first class of RLC series circuit, I told you that such type of circuit is widely used in TV receiver or radio receiver for the purpose of selecting a particular frequency station or channel. To select a particular frequency channel or station, you need to design a selective circuit which can select that particular frequency range, irrespective particular frequency range than others. Okay, so that's why we will choose a narrow band, very narrow band selective circuit. Narrow band selective circuit, that means sharp curve. We will choose the curve corresponding to R value is small. R value is small, very sharp curve. The sharp curve will give you the narrow band range. Now I will tell you the half power bandwidth. The half power bandwidth half power means what? The power becomes half at this point. If you consider the current versus frequency curve, then you can find out 2 points on this curve where the current becomes 1 by root 2 of its maximum value. Let me repeat this point. You can find out 2 points on the resonance curve at which the current of the circuit becomes 1 by root 2 of its maximum value or power becomes half of its maximum value. You know power equal to P equal to, tell me in terms of I square VI B equal to I है तो I square R you can write. Okay, power equal to in terms of current we can write I square R, or in terms of voltage we can write V square by R. Okay, now if this half power, before define it, let me tell you half power points. What is half power points? Half power points. Half power points. There are 2 points. Okay, 2 points on the resonance curve where the power of the signal power of the power of the circuit becomes half of its maximum value. The half power point defined as the points, okay, the points, the 2 points, the 2 points, half power point actually 2 points on the either side either side of either side of resonant frequency, resonant frequency frequency where the current or power, where you can write in terms of power, half power, where the power falls to, half of its maximum value, half of its maximum value. Okay, any doubt? Maximum value, the half power point are the points on the either side of resonant frequency where the power of the circuit becomes half of its maximum value. If maximum value is P max, at this point the power will be P max by 2. P max, you can define it on the resonance curve in terms of current. If I write in terms of current, then you can write where the power in bracket you just write current, it's better, power or current falls half of its maximum value. For current's case, you write 1 by root 2 of its maximum value. 1 by root 2 of its maximum value. You know power, and this by this relation P equal to I square R, the half means what? 1 by root 2 falls to half of its maximum value. For current case, this will be 1 by root 2. If we consider current, it's actually confusing. You write it in different ways. You make it another statement. It's good. Half power point. Let me write it again. You can write in terms of current or voltage, no problem. 1 by root 2 of its maximum value. Okay, any doubt? No. Now you need to calculate, and the corresponding frequencies are known as half power frequency. And now you write here the corresponding frequencies, half power frequency, half power frequencies, the corresponding frequencies of half power, the corresponding frequencies of half power are known as half power frequency. Okay, any doubt? Half power frequencies. Now if you denote it F1 and F2 half power frequency, F low and F, you just write F low half power frequency, FL HP, and F high on both sides of resonance frequency. Therefore you will get a low half power frequency and a high half power frequency. So bandwidth, resonant half power bandwidth will be equal to the difference of half power frequency, higher half power frequency minus lower half power frequency. Lower half power frequency. You just make it as a subscript format. As a subscript format, it's good. The half power frequency, you can write like this: low half power frequency and high half power frequency equal to. So this is actually low half power, high half power frequency, and this is low half power frequency. So you write it here: high half power frequency minus low half power frequency, low half power frequency equal to like this. So now, okay, bandwidth of the upper bandwidth of the circuit. Now we can define or derive an expression of half power bandwidth in terms of resonant frequency and also quality factor. Quality factor, how much time remaining? Quality factor, let me tell you, quality factor actually nothing but the ratio of inductive reactance and resistance, or capacitive reactance and resistance. Okay, you can define it. We can define quality factor or Q factor in different ways. One of them is Q factor equal to omega L by R. Omega L for inductance, omega L by R, and Q factor we can write also 1 by I will prove it, or you can prove it yourself, no problem, but 1 by omega CR, okay. This is the Q factor for inductor and a capacitor. Okay, Q factor. Okay, generally we can write the voltage across capacitor and inductor at resonance case is equal to Q factor times of supply voltage. Okay, that's why this circuit is known as voltage magnification circuit. Okay, you can write voltage drop across V inductor equal to Q factor into supply voltage, and you can write the voltage drop across capacitor is equal to Q factor time into supply voltage. You just prove it yourself. If you face any problem to prove this thing, you just inform me. I will help you to derive this thing, or if possible I can derive this thing in next class. Okay, actually I will discuss in next class about two-port networks. Okay, and that time I will try to derive this expression if you face any problem. Less is R, more is quality factor. Yes, actually quality factor, you see that Orkodeep, that ratio of energy stored by energy dissipated, we can say, because you know that capacitor and inductor are energy storing element. you know these two elements store energy and resistor dissipate energy. So stored energy divided by dissipated energy. So if dissipated energy is high, R is high, then quality factor obviously it is small, actually becomes small. So therefore it's also related to half power bandwidth. We have seen that half power bandwidth changes with value of resistance, and quality factor is also changing with the value of resistance. So therefore there is a interrelation between quality factor, resonant frequency, half power bandwidth. I suggest all of you please read this interrelation between quality factor, half power bandwidth, resonant frequency, half power power, half power, resonant power, and other power. Okay, you read it, you derive it yourself. If you face any problem, I will tell you. Otherwise, I will repeat those things in next class before going to discuss about two-port network. Actually, in next class, I will discuss in details about two-port network. Okay, and I will provide you some problems as assignment. You will solve yourself and submit it within the deadline. Okay, and I will provide you the RLC series circuit PDF by today night. Okay, I will send you, don't worry. And if you have any doubt regarding the series RLC circuit or conventional RLC circuit, whatever we have discussed so far to calculate the transient response and steady state response for a RLC circuit, can you tell me anyone what is the difference, exact difference between uh, that circuit to that circuit which one we have used to calculate the transient response or steady state response, and the circuit which one we have used here? Both are series RLC circuit. Okay, but what is the what type of change actually we have considered here? Previous case, when we have derived the transient response and steady state response of a series RLC circuit, that time we have considered a DC supply voltage. That means the resistance of the supply voltage is fixed. But now we have considered a AC supply an AC supply voltage. The frequency of the supply voltage is changing with time. Okay, and this is very important circuit to select a particular frequency among a number of frequency components. Okay, thank you. Thank you everyone. If you have any doubt, write it. Okay, hope all of you understood the concept of series resonance, quality factor, half power bandwidth, half power point, half power frequency. Okay, and let me ask you one question, you solve it yourself, and in next class you tell me the answer. Why half power point is also known as 3 dB point? Minus 3 dB point. What is minus 3 dB point? This is for all of you. What is minus 3 dB point? Okay, what is minus 3 dB point? You solve it. You just take log, you just express the word in terms of dB. Okay, in terms of dB, then you will get minus 3 dB. 1 by half equal to, you will get minus 3 dB if you express is in dB unit. Okay, dB you know na, decibel, audio intensity, intensity of our audio sound is measured in dB unit. Sorry, decibel in dB, right? In decibel unit. dB means decibel. Okay, so you express the power half in terms of decibel unit, right, Saiva? Then you will get minus 3 dB. Half power points are also known as minus 3 dB point if you express the power in terms of dB. Okay, thank you everyone. Let me stop here today's lecture. Okay, if you have any doubt, you can tell me. Okay.